So we look at that and we start thinking of what is happening in a solid state. And so in the solid state, we have to have atoms move. We had it in the same way in a gas, but we know that the mean free path for the atoms to move is much larger in gases or liquids than it is in a solid. So we must be able to break bonds and reform them. That's where the temperature comes in. So one way to look at how atoms move and what atoms require is there's an energy barrier that's required for atoms to move. If we go back to the last lecture where we talked about the equilibrium vacancy concentration of the number of equilibrium vacancies at a given temperature, there was a value Q in the Arrhenius relationship, which we call the activation energy. Now, if we look at this small, simple schematic plot, that activation energy is this energy barrier. So we must roll the rock up the hill like Sisyphus in the Greek mythology. Had to roll the rock up the hill, but he could never overcome the energy barrier, so the rock rolled back over top of him every day. And his job was basically to try to roll the rock up to the top of the hill, which he never could do. Now, that's not the case in diffusion because the atoms will get over the energy barrier and they'll be able to move. So as we start looking at it, as we get to the energy barrier, the atom will move into that other vacancy. And so it's that activation energy or that energy barrier that we have. So we must be able to overcome that. And we typically overcome that by the addition of heat or an increase in temperature. Now, brings us to another issue. It's almost sort of like the riddle of if a tree falls in the woods, does it make a sound? Now, if we have a pure metal, all the atoms are the same. So how do we know they're exchanging positions? There's no compositional changes. There's not that much driving force. And what we call this is self-diffusion. Because we are heating it up, we know there's vibrational energy being applied on, in this case, this copper piece of metal. So the atoms themselves should be moving. We know as the temperature increases, we're creating vacancies, so there should be atomic motion. My question to you is, how do you know? Because if it is science, we are supposed to be able to provide evidence for this. I'll give you a little second to think about that, but one way to do that is to look at and label atoms. So if we were to be able to track individual atoms, we would see that A, B, C, and D, if we just choose 4 atoms in general, they would move after some time, even at room temperature. That it would take that amount of time is much greater at room temperature, but if we add some heat to it, we increase the temperature. Say we go in a steel up to about, or let's say copper, we go up to about 700 or 800 degrees C. These atoms will be moving around because we know that vibrational energy of the atoms has increased. But how do we track them? And that's typically done if we go back even into lesson 2, a little earlier in lesson 2, we talked about isotopes. And if we can put radioactive tracers of the same element, just a different isotope that makes them radioactive, we can track where atoms move. And that's in a lot of cases how self-diffusion coefficients are determined in different materials. It's for the most part the same atoms. We need to find some way to track them and what their movements are, and we can determine that primarily through the use of these radioactive tracers. Now, a more common issue where we're going to see diffusion, and one of the driving forces for diffusion, and we're going to see this, is a concentration gradient. So if we take what we call a diffusion couple, and what this diffusion couple would be in this case is copper and nickel. We're going to take 2 pieces, one piece of copper, one piece of nickel, and put them in intimate contact. Now, if we just put that in intimate contact at room temperature, the copper is going to stay with the copper, the nickel is going to stay with the nickel. We're going to have a very distinct interface between the two. As we see here in our concentration, if you look at the concentration of nickel and copper as a function of position, they don't change. But what happens is we raise the temperature. Now, just like with anything else, we have copper atoms and nickel atoms that are segregated. As we increase the temperatures, the copper atoms are going to want to move into the nickel. Now, we chose copper and nickel here for one primary reason, is they're completely soluble in each other at all compositions. They form a solid solution. They're a fairly unique alloy system, but it's also an industrially important alloy system. And I will talk about this, that if you want to gold plate copper, you need to add a small layer of nickel on top of it in order to gold plate the copper. And so what you will typically see is they call it a nickel flashing in the electroplating industry. And so copper in contact with nickel is a commonly encountered diffusion couple. Now, what will happen as you increase the temperatures is some of that copper will diffuse into the nickel and vice versa. Now, they diffuse at different rates, so you're not going to have a distinct interface anymore. What you're going to have is really an interfacial area. And if we were to take the concentrations, we see that it's no longer this sharp interface. The copper has diffused into the nickel and the nickel is diffused into the copper. Now, in this case, the schematic shows them diffusing at basically the same rate, but we know that's not quite the case. But they're intermixing. And if you really start thinking about it now, what we have is we've formed a solid solution in between just through atomic motion or diffusion. Now, what if we simulate this across a barrier? Now, this goes into another issue. Now, we had not talked about the time frame involved, but in this case, if we were to try to simulate the atomic motion, we know that the interface does not become, it's not uniform. So it will blend together. It will be not a stark or a distinct interface after some interdiffusion across there. So with this substitutional diffusion, because what are we doing? We're substituting, we're looking at the substitutional atoms in the crystalline lattices. So if we go back to our crystalline defects, there are no interstitials here that we're talking about. These are strictly one vacancy jump to another. And we know with the temperature that we're going to increase the number of vacancies. But there's a theory for diffusion called random walk. And what that is for the most part a statistical look at how an atom, or what the chances are that an atom will jump to a vacant site adjacent to it. And it's purely statistical. And what we tend to see is that that's why we have this non-uniform interface across there. So we have vacancy concentration, and this frequency of jumping will be determined by this random walk theory. Now, that's down at the atomic level, and that's all well and good to have an understanding of, but what are the diffusion mechanisms we're mostly worried about? As we saw with the nickel-copper system, vacancy diffusion, where we have an atom from one of its typical or normal lattice sites jumping to an adjacent vacancy. In a lot of cases, there needs to be a vacancy close by that's going to determine it. And for the most part, the atoms and the vacancies are just exchanging positions. So the atoms will diffuse one way, the vacancies will tend to go in the opposite direction. And these are what we call substitutional atoms. So we have one atom moving into the vacancy within what we consider that typical crystalline lattice. Interstitial diffusion is a little different. And what you can almost imagine is it's a little simpler. And so you have a position of an interstitial atom. Before diffusion, it will move to another interstitial space. And notice how much smaller the interstitial atom is than the substitutional atoms that we have. So these small interstitial atoms can diffuse rather rapidly across there because it doesn't really need to wait for a vacancy. There's a lot more vacancies with the interstitial spaces. It can easily move between the atoms. And so they're smaller, more mobile. So interstitial diffusion tends to be much more rapid than substitutional diffusion. I like to compare it as if you've ever driven in California on some of the freeways. And typically when you're driving in California, you're going to run into traffic jams. And you'll be sitting there in your car. And if you imagine the cars on 5 lanes, both directions, being stopped cold, just no movement, 5 o'clock on a Monday or Tuesday or whenever, and the motorcycles will come up the white lines. And so if we think about the white lines, they would be the interstitial spaces. So we see that the motorcycles will drive up between the cars on the white lines. And so it's very much the same thing. So they can work their way through traffic jams much more easily than a car, because a car trying to sneak onto a white line or sneak between a couple lines is going to cause an accident. It's just too big to sneak through the interstitial space. Motorcycle, on the other hand, can easily do that. And so it's another sort of way to look at interstitial diffusion. Now, so we have our 2 mechanisms. What we haven't done is mathematically define what diffusion is. And so we do that for the most part, through a definition of what we call a diffusion flux. Now, diffusion is time dependent, So we want to know what the rate of mass transfer is. And so this mass transfer is typically defined by a mass diffusing through a unit cross-sectional area per time. So imagine a plane transverse to the direction or normal to the direction of your atomic movement. And so we want to define the number of atoms moving through that plane. It's a given size of cross-sectional area over time. So we have our diffusion flux is basically just mass divided by the area, cross-sectional area, and the time. And so we call that diffusion flux. And if we're going to take that a step further, we start thinking in terms of steady state. So one way to look at it, and one way that we're going to really look at diffusion the rest of this lesson, is really gaseous diffusion through a metal plate, where if we take a metal plate, imagine we can put this between two different gas pressures. So we have a pressure that's greater, a pressure A on one side of the plate, a gas at a pressure B, which is less on the other. The concentration gradient between A and B for this gaseous species is going to be the driving force. And I will write, it's written down on a following slide, but I think it's so important that I'll repeat it here again, is that the driving force for diffusion is a concentration gradient. So if you've taken heat transfer classes, you will see very much the same equations for heat transfer as you see for diffusion. In heat transfer, thermal gradients are the driving force for heat transfer. And in this case, we're more worried about concentrations. So if we would take and hold constant these two pressures, not worry about time of this metal plate, the gas would diffuse from the higher pressure to the lower pressure. And what we tend to see is we would see this concentration gradient over time. And we notice that it is linear between position A and position B. And so we have the concentration of A at the surface, the concentration of B at the other surface. So over time, holding these two pressures constant, we're going to get a linear distribution of concentrations as a function of location. This is defined by Fick's first law. So this is our first time running into a partial differential equation in the class. This won't be the last. And so this flux in Fick's first law can be defined by what we call a diffusion coefficient multiplied by the concentration gradient. So the negative sign tells us that the diffusion direction is always from high to low. That's that concentration gradient. Very much like being in a crowded room. If you're in a crowded room and the room is packed, what do people want to do? People want to leave that room. You want to go to a place where there's less energy per se. And so you'll go to the next room or an adjacent room or leave that. And so atoms do much the same thing. If they have a higher grade, if there's a higher concentration of atoms in one place, they want to move to an area of lower concentration. And so that's what the negative sign is telling us. My next question is, we've been talking about temperature being important. Where is temperature? And where is time? There is no time because Fick's first law is defining the steady state diffusion, where diffusion flux does not change with time. What that, for the most part, tells us is this is what we would see at what we consider steady state or something close to an equilibrium condition because there is no time. So at the end of where we would expect things to occur, that's where we see this type of steady state behavior and linear concentration gradients. But once again, where is the temperature? The temperature will be in the diffusion coefficient, and we will get to that as we move forward. So let's look at a simple steady state diffusion problem. And this one, the concentration is a little different than what we've seen before, but that's not to worry about here. Where we're really going to concentrate on here is solving for the diffusion flux. And what we want to do here is use Fick's first law to define what the diffusion coefficient would be. And so one thing I'm going to bring out is I will be identifying iron as BCC and FCC. Now it's important to note that above a certain temperature, iron goes from a BCC to an FCC crystal structure. And so the diffusion coefficients and the diffusion parameters that we're interested in change as we change that crystal structure. So as we move forward and we talk about iron, make sure that you have the correct crystal structure for the iron identified. And so we have a 2 millimeter thick sheet. We're going to expose it to a carburizing gas, which means it's got a certain amount of carbon in it on one side, and what we consider a decarburizing atmosphere on the other. And typically what we'll see there is something that will be in lower carbon concentration on the other side. Both are at a temperature of 675 degrees C. We know what the carbon concentration is on both surfaces. So we want to be able to get the diffusion coefficient if we know what the diffusion flux is. So we know from Fick's first law, we have our concentration gradients. We know the thickness. And so we need to keep track of our units when solving these. So if we know the flux, we know this is in kilograms per meter squared, which means we need to convert all of our other values to kilograms and meters. And so what we see is a diffusion coefficient about 2.3 times 10 to the negative 11 meters squared per second as we walk through the calculations, or we plug and chug through a rather simple equation. One thing to note, and if I were you, I would write down, is that units for diffusion coefficients tend to look like this. They tend to be very small, 10 to the negative 10, 10 to the negative 11, even 10 to the negative 12 as far as the scientific notation for them. So always keep that in mind when you're calculating diffusion coefficients or you see diffusion coefficients. They are small numbers. So we see that we can figure out, based off the flux and diffusion coefficient and concentration gradient, I should say, what the diffusion coefficient is.